Sorry, George.
Good. This one? Don't worry about it. I'll take care of it from here.
Okay, everyone. I think we're running about 15 minutes behind on time. So lunch, I believe on the agenda is scheduled for 12:15. We'll just start it at 12:30. And other thing I want to point out is for Q&As, there's also a Slido that we're using, which you can access through the QR codes that are on every table. So you can just scan the QR code. It'll take you to a website. It'll say Q&A via Slido, and you can just put your questions directly in there if you don't feel like coming up to the podium, to the mics around the room and ask those questions. So we'll monitor those questions. We'll try to get to them as well. But for the next keynote, I'm pleased to introduce Dr. George Pappas, who is the UPS Foundation Professor and Chair of the Department of Electrical and Systems Engineering at the University of Pennsylvania. He also holds a secondary appointment in the Departments of Computer and Information Sciences and Mechanical Engineering and Applied Mechanics. He has previously served as the Deputy Dean for Research in the School of Engineering and Applied Science, and his research focuses on control theory and in particular hybrid systems, embedded systems, hierarchical and distributed control systems with applications to unmanned aerial vehicles, distributed robotics, green buildings, and biomolecular networks. His talk today is titled Safety Autonomy with Learning in the Loop. And with that, I would like to welcome Dr. Pappas to deliver his keynote.
Thank you very much, Vishal. It's a great pleasure to be here. I'd like to thank the CPS program, the program committee, for inviting me here. I'd like to thank CPS program really for the support more or less throughout my career. It has been very important for me, and hopefully it's going to be very important for your careers as well. This is sort of a new building. We're building on AI, and it will include a new center on safety and trustworthy AI, which is led by Professor Rajiv Allur, known as the Asset Center. I'm also a member of the GRASP Robotics and former director of the GRASP Robotics Center. Above all, I really have to thank my collaborators and above all my students and my postdocs, current, former, for bringing me to this state and also contributing to pretty much everything that I will talk about today. And a lot of the results I'm going to talk about come from this CPS program in collaboration with my colleague Nick Matney and Kostas Danilidis. The context that will motivate some of the questions that I'm going to talk about today comes from the area of autonomy. If you look at sort of robots, I would say the past 40 years, they have been inside industrial and manufacturing lines in very structured settings, and that gave us certain abstractions to work with. However, now, primarily because of enormous advances in sensing, computation, and now machine learning, we feel confident about getting robots out there, making maps of the world, sort of trying to navigate outside, and then do interesting autonomous sort of behaviors for all kinds of applications. Of course, the most famous one may be the sort of the self-driving one, But there are many other things that we already saw to some extent in some of the earlier presentations as well. That said, despite a lot of investment, also industrial investment, there has been also realization that autonomy is also hard. Okay, and I think that creates an interesting problem for the CPS community. In one sense, there's a lot of industrial interest in this space, but there are also hard problems that I believe that the CPS community is uniquely poised in addressing over the next decade, and have both scientific impact, but also have impact in making the autonomy vision a reality. More technically or architecturally, I think the CPS program has always been one that brings disciplines together, tries to understand interfaces across very different components, whether that is control and computation, as we saw in the previous frontier, control and communication. But now I think the new component that everybody has talked about, Jack talked about as well, is very much to bring learning into the control loop and really reason about cyber-physical systems that have a large amount of learning-based components, and really to think about how do we think about systems like this. So I do think that safe autonomy or similar types of systems present a great refreshed vision for the future of the CPS program, where we really think about cyber-physical systems with machine learning in the loop. So for example, in this particular case, you can see that you may have a robot operating outside. It uses deep learning. It may also use other modalities like IMU or LiDAR, but the deep learning and vision-based perception is the new modality that we use to create perhaps maps and do scene understanding, and then do planning, safe planning in them. So I'm going to use a little bit this architecture to motivate some challenges, and that will be kind of a technical outline for the rest of the talk. So if I look at some concrete technical challenges, and some of these have already been mentioned earlier, if you look at the deep learning component, as Jack very well mentioned, when you get the systems out there, they are not very robust. You train something in the lab, you send it out there, and there is a mismatch in quality in what you see between train and test time. And in addition, there has been the famous Panda example that has shown that it's very easy to fool deep networks and make them misclassify things easily. However, in addition to this more adversarial mindset, there are other more natural type of perturbations in the sensors, such as, for example, changing the lighting, that can cause things not to work very well. And these are much more realistic, the kind of things that you may see in practice. So I think making machine learning more robust is one of the key things if we want to see machine learning being deployed in more safety-critical settings, which is the cyber-physical setting. The other thing, from more perhaps the control point of view, is that, or a planning point of view, depending if you come from the robotics community, we are no longer planning inside the lab or inside manufacturing labs where things are very structured. The environment is not that structured. This is your perception of the world. This is what deep learning gives you. This is what perceptual pipelines give you. And now you have to make safe decisions with this sensor modalities. Okay, so I think the question is, how do you take this data? How do you interpret it? How do you get not only estimates of the world, but the error bars that, again, Jack also mentioned, and then think about planning, with safely in such perceived environments. Okay, that's another challenge that I see going forward. Perhaps from a planning and control community, we have been working with safe assumptions, Kalman filters, and so on. But now we have very different sensor modalities, and we need to change the way we think about planning and control and bring those in. And then the third topic I will touch upon today is you know, you have the machine learning group training a deep net with 1 million or 1 billion parameters these days. You have the control group that may be using learning or RL, whether it's deep RL, imitation learning, or a standard controller. You put them all together and you get something that you cannot really reason in a compositional way and certainly cannot really verify in a scalable way. And I think that's another challenge really for our community about how to sort of really address the verification and get safety assurance, other types of guarantees, formal methods for systems that look very much like this, where you may have a large deep net, perception deep net in the loop. So given this kind of context, the intellectual context out there, I'd like to talk about 3 challenges that sort of our group has been addressing in the context of this CPS project. The first one, it has to do with deep learning and how to make it robust, not necessarily to adversarial perturbations, but rather more realistic shifts you may see at test time. And this is something, again, even though I'm talking about autonomy, the same kind of challenges Jack kind of mentioned in the ambient intelligence for healthcare are, you know. So these are truly cross-cutting type of problems. The second one is to think a little bit some new work that we're doing on sort of how to bring some of these deep learning uncertainty into the planning and the control loop. And then the third one is how can we think about verification in a more scalable way, which can sort of give assurances of the holistic closed loop system. Okay, so that's essentially the outline of my talk. The first part is going to address deep learning with robustness to environmental shifts. This is largely the work of my PhD student, Alex Roby, who's co-supervised also with Hamed Hassani, a colleague in my department. So as I mentioned, what you see, you know, since the last 5-6 years, there has been a lot of effort also from our community, and we should be very proud of that, on sort of trying to make the machine learning more robust. And this is sort of motivated by the fact that deep learning is very fragile. There's the famous example that you can have unimperceptible noise that you cannot really perceive, and you know, yet you can sort of fool the classifiers. And I think that makes you know, machine learning not robust. Now this, to some extent, led into 2 paradigms of how to address this fragility. The first paradigm is, you know, train deep nets to be more robust. And that is the robust adversarial learning, which is sort of the top approach, where you take your data points, you know, X star, you add some, you know, bounded perturbation. You take at every pixel and you just sort of perturb its values by a little bit. And then you try to learn learn classifiers that are sort of robust to that type of perturbation. Okay, and that is very much motivated by the fact that, you know, if you add a little bit of noise, you want to be robust to a little bit of noise at every data point, at every pixel, if it's an image and things like that. The second approach, which comes more from a verification formal methods sort of point of view, which is after you have trained your deep network, you give it to a verification engineer, formal methods engineer, and they take the neural net, they add a perturbation, they push it through this set through the neural network, and they try to see where it is on the output, and hopefully when you pass all the set of the data across the neural net, you end up getting the same classification. So you verify that you are sort of robust to these type of perturbations. Okay, so, and I think especially the second part, the bottom half of that of the slide, is where I think our community has done lots of work. To some extent, we're leading this effort in the sort of the trustworthy AI kind of area. Now that said, I would like to consider moving a little bit away from adversarial perturbations, which may be very important in an adversarial setting, in a security-minded setting. So if you are very much into security and attacking AI, that is very important. But if you're interested in the kind of things of how do I make more robust deployments in realistic environments, to motivate a little bit the kind of things that can happen, I'd like to give you the first example, which comes from Chelsea Finn's group at Stanford, where you can train your DeepRL controller to manipulate certain objects sort of on the left, and you're happy, you get some performance like 86%, and you claim success that this is happening. And then what happens is that when you deploy things, slight changes in the lighting drop the quality of your machine learning approach from 86 to 32%. If the objects are transparent, again, things don't work well. If you have a background change on the sort of the plate that you do things, again, significant drop. So these are very significant drops in performance of the machine learning of whatever your approach is. And these are not necessarily the sort of the adversarial attacks, but these are actually realistic shifts in the data that you may see in deployment. A similar type of thing, much more in the context of autonomy, happens when you see, for example, you train on sort of this is the so-called traffic sign recognition data set, where you try to detect traffic signs, very relevant for sort of a self-driving vehicle. And you may train on data that may be on sunny days, but then you may test on sort of snowy days or foggy days or rainy days. And you can see here there's like sort of 4 levels of hardness of the data, that as you go from sort of level 1, which is modest snow, to level 4, which is sort of a blizzard conditions, you can sort of see the monotonic degradation in the performance of your machine, your detector. So this means that your detectors are very fragile to very realistic things that you may see in practice. And I do think that it's a sort of an opportunity for our community to sort of really start transitioning from the more sort of mathematically appealing sort of adversarial examples, which come with norm-bounded sort of perturbations of your data, to much more realistic shifts you may see in the data when you operate in the real world. Okay, so the first topic is very much like I would like to propose is how to make machine learning more robust, not to sort of the data to sort of norm-bounded perturbations, but rather to real-world distribution shifts. And this is sort of what we have been doing a little bit over the pandemic, really, which is, when you want to be robust to some shift you may see in the environment, as Jack mentioned again, it's good to have some model of how that shift is, and you use that model, incorporate it to make your machine learning more robust. So what are the kind of shifts that may happen? What we call them models of natural variation. Some shifts you may know a priori. You may scale the image. You may change the resolution of the sensor. You may rotate the image. You may flip the image. There may be invariant other types of symmetries in the image. Those are kind of shifts that you may know. And you can have a function that takes your data point X and sort of rotates it by delta, for example. In this case, you have a model of how the data may be changing. This model is known. It's just a rotation matrix. And you may want to use it. You may also have physics that changes the data, and you may want to use the physics into the machine learning, as was mentioned in the previous Frontiers talks as well. But some of the shifts may be harder to model, and that is, for example, you train during sunny days, but then you test in rainy or foggy days. Okay, this is much harder thing to model and get a sort of a functional form of what that distribution shift may be. So, but let's assume for now that we have such models. In the top case, that is kind of given, and in the bottom case, I'll tell you how we learn these distribution shifts, okay? So we will have a 2-step approach to address this problem, which we call model-based robustness. There's another one we call model-based generalization, which is we have the first step here is to learn this model of variation if we don't have it, and that is we we sort of take an image, we learn this model, and I'll tell you again how we do it, which takes a data point, like an MNIST digit 3, and then we, for example, are allowed to vary its background, okay? Or its color, or scale it, or something like that, okay? So we have a couple of knobs, and by changing these knobs, we hallucinate about the same data point, but in a variety of other settings as modeled by this model variation. And then we take this model and we plug it into an adversarial training framework, which is a min-max game theoretic thing, where the inner maximization basically says, you have this data point 3, let me pick the harshest variation of that data point in sort of this, using this hallucinated data, and let me try to train my predictor so that it is robust to those harsh variations of the data that you have. Okay, so we use the models essentially to sort of be robust to variations that which the model sort of predicts we may see in the data. Of course, it's up to you to have a sense of what are the kind of models of variation, and that is a discussion. If you are sensitive to lighting, then you need to develop sort of a model that changes the lighting of the data points, and then you train adversarially in a way that you can be sort of less sensitive to lighting variations. And that's essentially the key idea. Somewhat different but related idea is to generalize to backgrounds, across backgrounds, which is to think about, you want to learn a classifier, F, that is invariant across all background changes. Okay, so that's a slightly different thing. This is potentially something that may generalize also to backgrounds that you may have not seen. That's the hope. And you can see that here this is posed again as an optimization problem. But in this case, we have some kind of an invariance constraint. Okay, we want our predictor f of x to be the same regardless of whatever the background is. Okay, so we kind of sort of want to factor away background variations or any other variation you have affects your machine learning algorithm. Okay, so now how do we do this? How do we learn these models? A, and how do we solve the bottom problems? B. Okay, I don't want to get into the details, but for the first one, we are using these sort of cutting-edge, deep generative models. There's a variety of them. Now we're also trying out diffusion models, which essentially do the following. They take your data point on the left, and what they do is they do this disentanglement between the semantic part, which is, for example, figuring out what the sign, detecting the traffic sign, and the part that has to do, a low-dimensional part that has to do with changing the weather or the snow or the fog. And this is a controllable knob that we can vary, and as we vary, we get the same data point, but with different weather conditions, for example. Okay, so this would be a talk in its own right, how to do it. We don't necessarily innovate here. We use one of these standard generative models. But they do have to have this type of structure that you break really the symbol, the semantics from the noise. That's essentially what you're doing. Now, regarding the second part, those are also, there's an interesting papers to be written about how to solve in this adversarial way, either optimization problems that are associated with these sort of deep generative models, or how to sort of really think about learning, but with requirements. I think learning has been left a little bit unconstrained for too long. So whereas here, what we're imposing really is a requirement. In this case, it's an invariance requirement, but one can think of other types of requirements, safety, fairness. You can impose them as requirements, and then you can think about how do you solve those optimization problems, and that's a sort of a paper on its own, or a sort of an algorithm on its own, right, which was done in collaboration with my other colleague, Alejandro Ribeiro. Okay. A slightly different variation, which I'm going to skip in the interest of time, is to do it in a probabilistic sense. This is something that's coming up. But I do want to give you a little bit of a sense of how these deep generative models work, okay, because that is sort of the important. So here are two state-of-the-art hard data sets out there. The one is called WILDS and the other one is called PACS. And these are sort of the benchmarks for out-of-distribution generalization. Okay, these are as large as ImageNet themselves. And here you have the so-called WILDS data set for cancer. Okay, so here, this is the data that we have. And here's data we generate, and here the model of variation is different MRI scanners. You want to make your model less sensitive to different MRI scanning machines. Here we have agricultural data, as was mentioned earlier, and you can do variations for sort of, actually this is more of a temporal variation. You know, the data changes over time. Okay, and when you test this, okay, so here, for example, when we look at the traffic sign recognition, if you test, for example, on the harshest data, the category 4 or 5 data, which is the harshest data, there's no comparison. Adversarial learning, which is PGD, the one by that comes out of the MIT group of Alex Madry group, is, you know, it's not really the right type of technology because it's really addressing a different level of fragility, you know, the norm-bounded perturbations. Whereas, you know, and the same is if you use ERM or if you use empirical risk minimization, even if you add the data documentation, it doesn't really matter. It's like a significant leap when you use a model off the shift into your training algorithm. Okay, and this is the sort of the WILDS data set. This comes out of the Stanford group, which is looking at sort of cancer detection data. Okay, and again, you can see these are other out-of-distribution detection, and you can, for the last, I would say, 6 months, we were sort of the leading out-of-distribution detector for this data set, and we kind of gotten almost 94%, which means that you're now in sort of in diminishing returns territory as far as training is concerned. So these are a very, this is a very sort of natural way that if you know your problem and you know the model evaluation, you can make it much more robust to such variations. Now, if you have such models, you can also do certification or verification. Okay, so as I said earlier, there's been a lot of work, which is to verify, given a data point, and some norm-bounded perturbation to push it through the sort of the neural net and see what the output is, or whether you are sort of all on the same side of the classification boundary. But if you have such models of how, for example, lighting changes the image, or how sort of a new sensor affects your image, or how you rotate the images, you can actually use such models and then really push these sets through. And then what you end up getting is verifying not necessarily norm-bounded perturbations, but you can verify, and this is sort of joint work with Clark Barrett's group at Stanford, which is to take, for example, the original image, but then verify that the same image at much lower brightness conditions also gives you the same MNIST digit. Or you can do the same thing at CFAR. You can sort of change not necessarily the pixels one by one, but the whole lighting, and get to say, verify that this also classifies correctly. Here, you take sort of the MNIST digit 0, and you make it foggier. And you still sort of, you know, verify that this works. Same thing here as well. So this gives you sort of summarizing a little bit the first part of my talk. It kind of tells you a little bit that it's time, I think, for our community to move a little bit away from norm-bounded perturbations and really focus on the distribution shifts we may see in applications, whether it's autonomy, whether it's healthcare, ambient intelligence, or any other application we're dealing with. Exploiting models, I think, provides natural robustness and generalization. Okay, so you may be sensitive to the model you've chosen, but it is better than no model at all. And I think it's also natural to think in a more optimization way to how to do learning with safety specifications. And I know that there's already posters in this meeting about this. I talked about invariance as a specification, but there can be also safety. There can be also other types of specifications. And something I didn't have the time to talk about is the probabilistic framework, where we balance worst case and average performance, and you control really the risk of misclassification, but that would be another talk. So These are some ideas about how to make deep learning more robust in the context that you're operating and be robust to the sort of changes in the data you may expect to see. The second topic I want to talk a little bit about has to do with planning over deep learning uncertainty. And this is work primarily of Lars Lindemann and Jan Iskandaros, and you know, some others, but these are the key students for this one. So if you, as I said earlier, when you look at it from either a robotics or a control perspective, I think there's been a lot of work in the past 30 years, which is sort of, you know, I am in an Amazon warehouse, I want to go from point A to point B, I want to avoid obstacles, I know the environment, you know, well or partially well, and please go there, satisfy lots of, you know, safety, avoid obstacles, do LTL specs, whatever, all of those things. And I think we're good at that. But I think now what we are seeing, you know, in many of these things is we go to the wild, we know nothing, we learn a representation of the environment, it's uncertain, and we need to act safely in it. Okay, so for example, you know, here's the kind of LSTM that Waymo uses, which, you know, given where the car is, sort of predicts where nearby agents, cars, pedestrians, bicycles may go, and now your job is to sort of figure out how to go around it. So one particular sort of, you know, example that I would like to discuss a little bit is, for example, the case where you do have an LSTM here. Okay, so you do get some predictions about where nearby objects will dynamically move. Okay, so, and then what you want to do is use those predictions in a way from an MPC controller in order to sort of plan safely. Okay, so and this is sort of a recent paper that. Okay, so the key thing here is how do we incorporate things like LSTM predictions into a control design in a sort of a safe way. And the key thing that is missing in a lot of this is, again, what Jack said wisely, which is that we really don't have error bars for these LSTM predictions. And if we don't have error bars, then we do best effort design. Yes, on average, we may not crash, but we really need to know a bit more about the uncertainty of the LSTM so we can be much more certain about sort of the control doing something that is safe. So then the question then becomes, how do we quantify uncertainty of things like RNNs, LSTMs? How do we put error bars around them? And how do we use such sort of error bars or perceptual uncertainty for safe planning and control? Okay. So our key idea for getting error bars comes from an old tool that is getting renewed attention in the machine learning community, which is known as conformal prediction. Okay? And conformal prediction is really a statistical approach, is a simple approach, but it's a very powerful approach. And it is a good statistical way of getting uncertainty quantification for deep networks. Okay, so it is, you know, it's distribution free. We don't really care about how the data is distributed. We also make absolutely no assumptions about the predictor that we have. This could be an LSTM, it could be a convolutional RNN, your choice. It's not, because it's a statistical approach, it doesn't really affect it. What we do assume is that, you know, somebody trains it, gives us the LSTM, but then we have some kind of available, some kind of calibration data or validation data, which are IID, and they come from the same distribution. Okay, that's the key assumption here. There are, of course, variations to this framework when there's distribution shifts and things like that, which are being developed as we speak. And then what you get is a kind of a confidence interval. Okay, so given what the conformal prediction, which goes back really to a paper in 2008. Okay, so given a failure probability, that's your sort of tolerance that you may want to live with, you know, you construct sort of a prediction region so that your output is going to be in this, you have a validity constraint that your output will be in this set that you construct with some probability 1 minus delta. Okay? So given delta, you construct how big this set is. And there are some guarantees that these sets are not too big enough, but we can talk about that offline. So if you sort of look at an example that comes from another recent tutorial on conformal prediction, so here you have a very canonical squirrel. So you're very confident that it's a squirrel, so you actually get that, that this is indeed a squirrel, and it's zero, you're very confident about it. But for other cases where you may have occlusions, you may have half the image, you're not so sure. So you shouldn't just do your best and say, this is it. You should actually give a range of the possible labels this is and how confident you are in each of them. And then, of course, if that's not a good prediction, then you shouldn't use it. And I think that's this is the sort of now, the same thing you can do, that was for classification. You can sort of do regression. And just to give you a little bit of a sense of how simple this is, it's very easy to actually do, is you choose a certain non-conformity score, okay, your error if you like. Okay, so this is what you see versus what your neural network or LSTM predicts. Okay, and you have some calibration data or validation data, like 500 of them, or it's a significantly less data than the training data. And you plot the histogram of these non-conformity scores, that's what they're called. And if you want 1 minus delta, you do a little bit of an inflation because of the fact that you have a finite data set. And then you get this kind of this validity prediction. Okay, so this is the way of getting those kind of intervals of how to ensure that, yes, you get a prediction, but you also have a certain error bar around it that tells you how good or bad it is. Now, the choice of your predictor and the choice of the conformity score may affect how bad your regions are. This doesn't mean that your predictor is good, but it gives you a framework to assess how good your predictor is, okay, and how good the uncertainty measures you are. What we did is do more or less this, but for LSTMs. Okay? I don't have time to go through this, but essentially what we were able to do is take a social LSTM, which is used, for example, for pedestrian walking at intersections. We trained an LSTM, and then we used validation data from the same, and then we ended up getting a prediction guarantees that look now, the difference from regression or qualification is you look at over a horizon, a planning horizon of some steps, 30, 40 steps or something like that. Okay, and then you get a uniform guarantee. You have to be a little bit careful about the horizon that you pick and things like that, but these are all details, and this is a non-conformity score that we picked that works well. Now, does this work well? We tried it, I said, in a Carla simulator, and just to give you a sense, here in this conformal prediction, what you get is, if you look at sort of 2.5 seconds ahead, this is sort of the histogram that we created from the training, from the validation data. You get errors of the form, 0.1 beat, half a meter, 0.6 meters on a 2.5 second horizon. And if you look longer, 4 seconds, you're getting sort of errors of the form, a meter, a little bit more. So these are, and this is very basic. What we've done so far is very basic. We just started this, but these conformity, it's simple, it's powerful. You can do for large models, and they give you reasonable error bounds. These are somewhat reasonable. Okay, so again, this histogram depends also on the quality of the predictor, and I'm not so sure we also have the best predictor. So once you have these histograms, you can convert them into these sets, and then you can incorporate them naturally into something like an MPC framework. As you get data, here, you can see on the right a little bit how this looks. So here, this is now abstracted. The uncertainty sets are abstracted as a set. It's a time-varying set. And then you incorporate that into your MPC framework. And as you get more data, your uncertainty may grow or shrink. Okay, there are adaptive versions of conformal prediction. It's very actually natural to do this for online learning. approaches where you get sequential data all the time. Okay, and then of course there's one technical issue which we're still working on, which is ensuring that MPC is recursively feasible. Then you actually end up getting a safe path with probability 1 minus delta. Okay, so this is sort of a way that we can do it. And then again, here's now the integrated LSTM MPC pipeline together. We use the conformal prediction to get constraints into MPC. And on the left, you have sort of a more a realization, a new realization that you have not seen. And on the right, you have something, a different realization. And the theory, our theory predicts, we put delta to be 0.05. That means that we should have expect 95 out of 100 to be safe. And of course, this is a slightly conservative prediction, so we get actually better than that. Okay, so this gives you a way to sort of to translate, safety guarantees is from theory, but then to sort of see statistically how this would work in new realizations under the assumption that we are in the same distribution. That, then that's a different problem there. Okay, so this is sort of the same, and then the sort of now we're working on extensions on this, which is, for example, given an LSTM predictor, which looks at past observations. I think Jack had a very sort of a slightly similar architecture. Given observations, you do some prediction about what the future prediction of a car, a vehicle, your system may be doing. How do we verify that what we predict, the LSTM predicts, will meet a certain spec? Okay, so Jack sort of constrained the output to meet a certain LSTM spec. Here we don't constrain, we just verify. Okay, so we just verify, and there's two approaches. One is predict, so using conformal prediction, the future of the output, take these sort of predictions, push them through robust semantics, something that we do, and then and then we compute the sort of these, the semantics of this LSTM box. The other way is to go directly to the robust semantics, which we can discuss offline. A slightly different approach to the same thing, where we don't necessarily do LSTM and conformal prediction, and this is really the work of Yanis Kantaros, who's now at Washington University, is to really look at more semantic maps and uncertain maps, and take STL specifications. So basically all this, the deep learning and the mapping is really abstracted into some kind of a representation, which we call as a semantic map. I don't really have time to talk about this, but here is a different type of application where you have lots of UAVs flying in a city. The mission is sort of avoid red UAVs, eventually track certain UAVs. All I want to say is that this is sort of now rather, you can do it in a way that is sort of, rigorous. You can have the probabilistic guarantees, and you can incorporate in complex environments here with both geometric. Here the geometry is known, the city is known, but you don't know where the agents are, you may misclassify things, and you can sort of reason about these things on the fly. Okay. Okay, so I guess the take-home messages for the second part is that, there's uncertainty quantification for perception control will be very useful, and this was mentioned again earlier before. Statistical approaches or more recent ideas from conformal predictions could be a good way for our community to sort of bring guarantees into sort of deep learning systems or systems that use learning enabled components. And then, this will allow us to incorporate uncertainty into planning and control or in online monitors, which was the last part. The last thing I would like to talk about has to do with the fact that we would like to verify the integration of a system. So somebody trains a deep net, perhaps using what we did, or some other approach, and you get an LSTM or something like that. You design a controller using model-based, data-driven, it doesn't matter. You put it all together, and you want to be able to reason a little bit about the holistic system. Okay, so here again, this is work of Lars Lindemann and Mahir Fazliab before, Radoslav Ivanov before that, and also Matthew Cleveland these days. So now, in this sort of more integrated view, we have in the past proposed a couple of approaches. The first one is very SIG, and in very SIG, the key idea is essentially convert everything to a hybrid system. So take the neural network, translate it into, it's a ReLU network, it's a piecewise linear, piecewise affine thing, translate it into a hybrid system. You have a hybrid controller, you have a hybrid dynamics, compose the hybrid system, you verify using something like FlowStar or an SMC solver or something like that, or SMP solver, something like that. Okay, so, and this give rise to this tool known as VeriSig, which is sort of one of the main approaches that verify not just the neural network, but rather the integrated system. Another approach, which is based not so much on hybrid systems, but much more on convex optimization, is to over-approximate the neural network by a so-called quadratic constraint. Okay, so this, if you want more details, you can see here, but essentially what you do is you take a look at the ReLU nonlinearity, that's the only nonlinear part of a neural network, and you do a convex over-approximation of that, loosely speaking. You get a convex over-approximation of the neural network, which is coarse, you don't touch the linear layers, and then if you have something that is linear here on the controller or is non-linear, but you can sort of, again, over-approximate it by a quadratic constraint, then you can reason using semi-definite programming about the integration about, say, stability of deep RL or things like that. Okay, so that would be the other approach. Okay, so now, if you look at the kind of things, though, that sort of my colleague Nick Matney is sort of working on, I mean, he uses, for example, perception-based module, which is ResNet 18, which has 1 million parameters. And that's a small neural network these days. Okay, so that's a very small neural network. And then, you know, he also uses machine learning or imitation learning or other approaches to learn a controller or a CBF controller or an imitation learning. Or that could have another, you know, 500 neurons. Okay, these are usually smaller in the control side. So this could be a neural net, this could be a neural net. And, you know, if you put them all together, you have a very hard time finding tools these days that can verify to this scale of systems. Okay. And I think, you know, there has sort of been, in my view, the promising approach here is to go statistical. And I know that many groups in our community, Miroslav Pazic, you know, Desmond at the USC, Chuchufan, and others are working on sort of more statistical approaches that I believe hold, you know, promise to scale to autonomous, you know, larger scale systems, just like the conformal prediction type of ideas showed us. Okay, so what we have done is really look at sort of formal notions of risk. Which, you know, statistical approaches can tell you something about probabilities, but you may want to care more about things like tail events. And one way of reasoning about tail events is to think about formal notions of risk, which also allow us to reason about uncertainty from average to worst case. So what we have been doing a little bit is to look at sort of given sort of now a stochastic process, which captures the system and potentially the environment, and an STL formula. What we do is we look at a realization of the system, we compute the robust semantics of the specification, we look at another realization, we again, you know, compute the robustness of that realization, we do it for many realizations, we get a histogram of all these robust semantics. Okay, and then it's a choice of what do you do with all that statistical data. You can do a probabilistic argument, which is absolutely fine. Okay, or you can use one of those risk measures that focus much more on the tail, like variance at risk or, you know, conditional variance and risk, you know, and, you know, what we've been developing a little bit is this notion of, you know, risk-aware semantics for STL based on this notion of robust semantics, okay? And for some risk measures, one can be, you know, statistically estimate, you know, lower bounds and upper bounds for these risk measures. Okay, that's essentially also the more details you can find in the paper. Okay, so here's a sort of a case study where you can think of the imitation learning controller without ResNet, just full state. Another one is an imitation learning controller with ResNet 18. Okay, this is the large neural nets. You can have a control barrier function, a learned control barrier function controller without the ResNet and with ResNet. And then you can do this analysis that I presented previously of the integrated system. The specification is sort of the cross-track error on the lane. Okay, you can have other types of specs as well. And then you can, reason a little bit about the, about how the histograms of these look. And so you can see, for example, excuse me, when you look at these controllers, you can see, for example, the green, the red controller, which is the imitation learning controller with the ResNet 18, the partial observability, is to some extent the most risky controller. And the same, the CBF controller with ResNet 18 is better. But if you actually had full state information, of course it would be better, which would be the middle graph. But you can see in the middle also the yellow and the blue. You can see that the yellow is better on average. However, it also has a longer tail. Okay, so the CBF controller is better on average. That said, it also has a longer tail. So once in a while, it will be unsafe. Okay, whereas the imitation controller is worse on average, but it has a smaller tail. Okay, and this is the power, I think, that risk measures can provide, is that it can allow to reason you not so much just on average or in probability, but rather to look at sort of what you may care a little bit is more about these a small amount of rare events that may kind of get you off the track. And if you're interested about why this is happening, a lot of this has to do with the transient versus steady state performance of these two different controllers. That's the key insight for the control crowd. Okay, so we have done also other studies which have to do with F110, but with LiDAR models. There was also a DARPA assured autonomy underwater vehicle that we've used with these things. Okay, so I just want to conclude with this thing to say that I think statistical approaches do have promise, I think, for large-scale systems with complex perceptual modules, which are going to be a challenge, I think, for us. Risk measures can be useful. It's one of the ways that we can sort of reason about tail events. And what I didn't have the time to say, but there's a new paper in the AI Journal which has to do with that we can also compute risks in the context of distribution shifts. Okay, so there's something else that you can do which kind of ties to the first part of the talk. Now, I do want to say that for all of these, more or less everything I've said, there are toolboxes on GitHub. Okay, so you can, and not only that, all these toolboxes integrate well together. So there's, you can take the training and connect it to semantic SLAM, connect it to SafePlan, they stitch the software together and use it on your system or innovate on any one of those. Okay, and you don't have to build the rest. Okay, and as a demonstration, because as our program manager said this morning, David, that this has to work in the real world. This is sort of this pipeline working with semantic planning in the real world using the robots of my colleague Dan Kodicek, so that you can see a little bit the images on one side. You can see what the deep network detects on the other window. You can see the semantic planning and mapping. This is something I didn't have time to talk about. And then how the robot who was supposed to sort of track the human while avoiding all other obstacles that it has never seen before. Okay, and I'm gonna keep playing this, but you can sort of see this doesn't really know anything about the environment. It doesn't know anything about the obstacles. It has just some deep nets around that detect humans, human pose recognition, as well as other obstacles. What I would like to do is do these experiments, changing lightings and things like that, to really test the sensitivity to lighting conditions. But this just a physical demonstration that all this pipeline works well together, both inside as well as outside, which was the original motivation of this talk. So with that, and I know that given that we're late for lunch, I'd like to end here and thank you again for your attention. Thank you. Okay, I guess questions?
Okay. All right, thanks, thanks, George. Great talk. So I have a question about this paradigm shift that we are seeing in like some applications of machine learning, like natural language processing. So in these types of settings, like we are looking at internet large-scale data, and we're just throwing like a transformer at that large-scale data and hoping the best, right? So if you think about that paradigm, it's kind of like making its way down to our fields too. Like I see that in robotics, like a lot of folks are trying to collect large data sets and just train a transformer based on that. Yeah. So a lot of the robustness ideas that you talked about requires like good models, and I don't know how that would basically like translate to a giant like high parameter transformer. On the other hand, one could think about the data. So I was wondering like if you have any thoughts on data curation or how to think about safety of the data sets rather than like looking at the model.
I am using transformers, not for this one, but for other work, which has to do more with things like the dynamic evolution of PDEs and climate change and things like that. But I agree with you that it is one of the technology of the day. And I do think that we should be all using it, especially for the kind of large-scale type of settings and or spatiotemporal type of settings. I completely agree with you there. I do want my transformer student and Alex to talk about distribution shifts in transformers. That's a problem we want to work on as well. I do think that, and I think this is an interesting question, and I actually want advice on this from, I would like to know, in the context of images, or various examples like the cancer shift or medical imaging, the notion of a distribution shift, to me, has a very clear physical intuition. Okay? So it's like, okay, lighting changes, things like that. When you talk about dynamic data, time series data, I think the concept of dynamic distribution shift, I think I can mathematically understand it. Physically, I would like to better get a good handle so that I can get better models of these distribution shifts so that then I can couple it with transformers. That's one. The second one is a very good question, which has to do with, how do we think about quality of data? And how does this affect sort of our machine learning, whether that is for robustness, higher accuracy, limited data, less data, all those things? I don't have a good idea about that, but I do think that reasoning about the quality of the data sets and not just assume that they are there, and we just do the best we can, but rather we put requirements on data sets and then go from requirements on data sets to requirement of models. I think that to me sounds an interesting thing. I just don't know how to start with it. But I've had various discussions on this with many of my students. I just don't know how to proceed on that. But I agree with, these are great points. I mean, maybe you have ideas, but I don't.
Thanks, George.
Yeah.
Hi, George. Thanks for the great talk. I had a question on, so you were talking about there's these two differences between having adversarial robustness and then something that might be more semantically meaningful that you're trying to capture. Mm-hmm. At a certain point, you talk about having this generative model that captures nuisance as well and a latent representation. I'm just curious in general as well how you ensure that perturbations you make in that latent space that's is supposed to be semantically meaningful, how those perturbations are also ensured to be something that's also semantically meaningful or meaningful mm-hmm. in the real world.
Yeah, they don't have to be perfect. Okay, they just need to point you in the right direction. I mean, but the point is that that is a little bit the secret sauce of the approach. That once you get a good model, a reasonably good model. It doesn't have to be like a 100% semantically meaningful thing, but if you get a good model of lighting changes, now, you know, and that could be also, by the way, a simulator, okay? It can be anything you want. It doesn't have to be a mathematical model. It can absolutely be a computational model. It could be a nerf, you know, for if you, so as long, once you get that, I think I'm very confident the rest will work. But what you're pointing essentially that I think, you know, I always know that once we have a good model of the variation, I know that we'll be robust to it.
Thank you.
Okay, but you don't have to be too precise. You know, 50% accurate, 60% accurate. You just want to point the deep network in the right direction, essentially, rather than some other way. Yeah.
Thanks.
Shamali Chatterjee, very nice talk. So I had a question regarding the physicality of the robots. So your robots there reminded me of the Starship food delivery robots in Purdue. So I was wondering, like, some of the, in terms of the maturity of the physical robots, is there any kind of ability to repurpose some of these food delivery robots, et cetera, so that you can run your algorithms on the cyber side on these more mature physical infrastructures? I don't know if you're familiar with the Starship robots, but it just reminded me of these little food delivery robots that we have all over Purdue campus.
Yeah. Those. Yeah, yeah. I mean, I guess from our perspective, the robots are kind of abstracted as a library of primitives. You know, so if you give me in your robotic setting sort of here's the abstraction of the robot, here's some primitives, plan with those primitives, go forward, left, right, and then, you know, then I think we can sort of potentially, you know, that's essentially the level of abstraction we get. We don't go down into the encoders of the robot, or just, we don't go into low level. We just sort of assume the robot has been abstracted as a library of motion primitives, and then we plan with those. Whether that is a UAV and where the primitive is hover, or whether that is sort of a walking robot where you can say walk, or whether that's a driving robot, we don't really care. So that allows us the code to be much more transportable, I think, to other types of platforms. I don't know if that answered the question, but that's...
Yeah, sort of. It was more like, hey, I've seen these vehicles where your algorithms could come in really handy to put them on the
There is
robots.
an interesting problem, which is kind of a meta-learning type problem of taking a stack from one platform A to platform B. And how to tune it with minimal tuning, or like, you know, how to do it in a like quick learning, whether it's meta, transfer learning, whatever, one of those, or a domain adaptation, depending on which sub-community you come from. But there is an interesting problem there, which will allow code to be quickly transferred from one domain to another.
Awesome. Thanks.
I mean, the same thing happens in the MRI. You know, Siemens built an MRI machine, but then wants to map it down to variations across hospitals. And there is a sort of a problem there, a similar type of problem there as well.
We'll do one more question, actually, if you want to ask a question, and then we have some housekeeping to go over next, and then we'll disperse for them. So we can have one more question, and then a little bit of housekeeping, and then we can disperse.
So my question is, you're identifying distributions in real time using data, and then enforcing probability constraints. For example, in your in the second half of your talk, you talked about that. Mm-hmm. So, how do you guarantee that the controller doesn't fall into paralysis, where there is no control that will...
Yeah, it's a good question. So for example, as I said, the MPC assumes, you know, the way we have it now assumes recursive feasibility, which means that a solution exists. Your question is, what happens if a solution does not exist? We were discussing this yesterday. I mean, at the very least, you can get some... using, you know, the dual variables, you can get some kind of, you know, which constraints are the least violating, and start ordering, and maybe there are ethical questions there as well about which obstacle is more important or, you know, not so important. But I do another thing is to, you know, maybe assume something that's time invariant as something that guarantees feasibility, like you move slowly and then you only go fast on. I mean, there may be ways, but my answer right now would be, I don't know the answer, but at the very least I can tell you that if it's not feasible, I can tell you, what's causing the problem, and then try to see whether we can order things and maybe eliminate some constraints to make it more feasible. But it's not a satisfactory answer for now, but we can go that way.
All right, I think we're going to conclude the session with that, so a round of applause for our keynote speaker, please. And like I said, before we disperse, we're going to have a little bit of housekeeping about the workshops that will happen post-lunch. So I'm going to call Simone to just come and talk to us a little bit about that.
Hello everyone. I know I'm separating you for lunch, so I will be super quick. After lunch, we're going to have 5 exciting workshops. They're going to cover topics such as artificial intelligence for healthcare, ensuring trustworthiness in AI-enabled cyber-physical system, intelligent autonomous cyber-physical system, socially responsible human cyber-physical system, and a workshop on future of cyber-physical systems. So 3 of these workshops, the one at the bottom, are going to be in this room, while the first 2 ones are going to be one in a room downstairs and one in a room upstairs. So my suggestion is to look at the name of those rooms. You can find them in the program, and then look also in the program where the room is, so you can find it. I also have a message for the workshop organizers. After the workshops, we are going to have workshop report back sessions, so make sure that you write down the discussion and summarize it. Somehow it could be a little presentation, or you want to write on a piece of paper and just discuss it with everybody, so make sure you do that. And then finally, the workshops were supposed to start at 1:15, but since we're a little late, let's start at 1:30, and we should be fine. And finally, the workshop report backs was supposed to start at 3:30. Maybe we can start at 3:45. 45 minutes should be enough for the session. So enjoy the lunch, and see you later. Thank you.
Lunch will start now and is being served outside. Thank you.
Thank you.
And folks, please take your belongings with you. The rooms will get rearranged for the workshop, so don't leave anything behind. When you come back, you'll find the configuration quite changed here. So take all of your belongings with you as you go get lunch.